All right, everybody. What we're going to do today is examine some properties of DFAs as it leads into the pumping lemma for regular languages. The pumping lemma is useful as it can help us prove languages are not regular. It's probably the easiest mechanism to prove things aren't regular. There are some other mechanisms which are a little more powerful. The way we're going to start is we're going to look at a particular machine. You can pick your favorite machine and do this as well if you like. In this particular machine, the first thing I'm going to ask you is how many states does this machine have? And your answer is going to be 4. Pretty easy, right? A, B, C, and D. And then what I want you to do is look at some strings, and you can pause the video and make some strings. Make some strings of length at least 4, and then trace their route through the machine. In fact, like maybe on the side, if you pick a string like 0, 1, 1, 1, 1, 1, or something like that, maybe just trace the route on the side. You've got 0, 1, 1, 1, 1, and kind of make yourself a little picture that looks something like this. So go ahead and do that for a few. I'll pause the video here, or you pause the video here, and then we'll do that. All right, so here's a couple that we came up with just to start, 1011 and 01011. And what I've done is I've written the states down here. We can do a bunch more, so here's some others. What you'll notice is that as long as you've produced a string of length at least 4, you are going to see the same state twice. And if you did this little diagram here, what you're going to notice is that there is some sort of loop in the diagram. There's some point where you see the same state twice, and in order to do that, you had to kind of like go through the machine in such a way that like you looped back to yourself or something, right? So as long as you have a string of length at least 4, because every transition takes you from A to somewhere, the longest route you can have is length 3 before you must visit some other state again. And that turns out to be pretty critical. So it turns out if you have a DFA, then it has some number of states, and any string with at least length n will have to revisit some state in that DFA. And so this is an application of the pigeonhole principle. And the idea is that n symbols visit n plus 1 states because you start in some state. And why do we care? So why do we care, Doc? We care because that loop in our machine that we just found is something that we can exploit. So for our easy 2 paths here, when I see this route from A back to A, that is a loop in the machine. Or for this other easy string, it's 0, 1, 0, 1, 1. This loop that you're seeing here is a loop in the machine that we can exploit. And in specific, we could remove that loop from the machine, and we end up with a string in the language. So if we remove this loop, that's like not going from A back to itself, then we are still left with a string in the language. Or if we remove this particular loop, we're still left with a string in the language, 0, 1, 1. That loop is also a loop, and you can try that with some of your strings. Go ahead and pause the video and do that. I think that would be useful for you to kind of see how this is working. If it's not working for you, ping me. Let's figure out why. But that loop is also something that you can take more than once. So in the first one, we said, hey, we could take that loop a second time, or you could take it any number of times, really, right? So you could either not take the loop, you could take the loop twice, you could take the loop any number of times. Or in this case, in the 1, 0 case, we can take it twice, right? And we still produce a string in the language, because all we're really doing is going from B back to itself, and then we're finishing off this string. So we could do that any number of times, as you can kind of see here, which is really rather cool, because this is a property of our regular languages that we're going to be able to exploit in order to prove that our things are not regular once we get there. So we've only looked at kind of this one machine in this video, but you should go back and check a couple of your own favorite machines. And no matter what machine you pick, right, there must be this situation that after you touch n symbols, then you'll have to have visited n plus 1 states. And because your machine only has n states, you will have had to have touched one of those states more than once. And that is the basis of the pumping lemma, really, which is that there has to be some loop that we can exploit. One thing that I'll say here is that if you're looking at a finite language, so I'll skip past a couple of machines here. Oh, I've erased it. Okay, well, if you're looking at a finite language, you might find that there doesn't appear to be, here we go, no, I didn't erase it, here it is, right? You might find that there doesn't appear to be a situation where I can list a string that's length 3. And that's true. There are no strings of length 3 that this machine right here accepts, because the language is a finite one. It doesn't accept any strings of length 3. And that's okay. Our property isn't broken. Our property says if we can list a string that's long enough, then it has to have a loop. In this case, we can't really list a string that's long enough that's accepted, so this loopy situation doesn't really affect us. There is some loopiness that can still exist, and you can probably see the loopiness inside the null state here. But for the most part, we're talking about accepted strings when we get to the pumping lemma, so we're going to leave it at that. Okay, this is a short video. As always, make sure to be kind to each other, and in order to do that, you do have to be kind to yourself. And I'll see you all next time. Bye.